Good day everyone. Today we are going to discuss about Rsa Algorithm or Rsa Algorithm. But before that, let me introduce myself first. I am Annalyn R. Nicolas from BSIT 3A BPO. In my part, I will be explaining what is Rsa algorithm, what is asymmetric encryption, and RSA in data encryption. For the math of RSA, we have Miss Jane Zalul. For the steps in Rsa algorithm, key generation, public and private key, we have Miss Jovia Andres and Mr. John Edsel Plata. For the last, we have Miss Andrea Calamasa for explaining encryption and decryption function. What is RSA algorithm? Rsa algorithm or Rivest-Shamir-Adleman is an asymmetric cryptography algorithm. This means that it uses a public key and private key. As their name suggests, a public key is shared publicly while a private key is secret and must not be shared with anyone. RSA is the most common asymmetric encryption algorithm. RSA algorithm is named after those who invented it in year 1978 by Ron Rivest, Adi Shamir, and Leonard Eidelman. What is asymmetric encryption? Asymmetric encryption is a process that uses a pair of related keys, one public key and one private key, to encrypt and decrypt a message and protect it from unauthorized access to use. And asymmetric encryption must be both the keys must belong to the receiver. When using RSA for encryption and decryption of general data, it reverses the key set usage. Unlike signature verification, it uses the receiver's public key to encrypt the data, and it uses the receiver's private key in decrypting the data. Thus, there is no need to exchange any keys in this scenario. There are two broad components when it comes to RSA cryptography. We have key generation and encryption and decryption function. We have key generation, generating the keys to be used for encrypting and decrypting the data to be exchanged, while the encryption and decryption function, the steps that need to be run when scrambling and recovering the data.
We are going to look at the math of RSA. Factors number. Numbers you can multiply to get original number. Example, factors number of 12. 1, 2, 3, 4, 6, and 12. For the prime numbers, number whose factors are only 1 and itself, number divisible by only 1 and itself. For example, 2, 3, 5, 7, 11, 13, 29, 37, and 61. Semi-prime. Semi-prime numbers whose factors are prime numbers, products of two primes is always semi-prime. For example, factor of semi-prime 21. 1 multiplied by 21 is equal to 21. Another one is 3 multiplied by 7 is equal to 21. So the example of factor semi-prime of 21 is 1, 3, 7, and 21. The last is modulo, remainder division. For example, 5 is equal to 3. 13 mod and 16 mod 5 is equal to 1.
Rsa algorithm example and each step. The first step is the key generation. You need to generate public and private keys before running the functions to generate your ciphertext and plaintext. They use certain variables and parameters, all of which are explained below. So in generating keys, The first one is select two prime numbers, which is the P and Q. For this step, the first thing that we need to do is in generating a key is to select two prime numbers, which is the P and Q, where P is not equal to Q. In our example, let's just use small numbers so that we can easily understand and explain it clearly, because it's too hard to compute if we use large numbers. So our goal in here is to explain it clearly. And for example, our prime numbers, P is equal to 7 and our Q is equal to 19. And then the second one, or the second step, is to calculate the product, which is N is equal to P multiply it into Q. So for this step, calculate the product, so we are going to multiply the P and Q, which is our P is equal to 7, and then multiply it in our Q, which is 19, and we get the product of 133. So we are going to call this value as N. N is equal to 133. And now, this 133 is a semi-prime number, because this 133 comes from multiplying the P and Q. And then the next step is to calculate the totient. So it is P minus 1 multiply it into Q minus 1. So for the next step, which is to calculate this totient, so before we proceed, let us know what is totient. The totient function describes the number of values less than n, which are relatively prime to n. For the purposes of RSA, we're only concerned with values of n which are the product of two prime numbers, which is our P and Q. So let's proceed to compute the totient. So our prime number P is equal to 7 and Q is equal, and then 7 minus 1 is equal to 6, and then 19 minus 1 is equal to 18, and then let's multiply it 6 times 18, so we get the 108, and we're going to call this value T, or totient. So now we already have our value in our prime number, the product, the totient. We can now calculate the public key. So let's call it E. So in selecting a public key, it must be prime, it must be less than totient, and must not be a factor of the totient. So we have here number 29 as an example. So 29 is a prime, and it is less than to our totient, and it is not factor of the totient. So we have here our example, 108 mod to 29 is equal to 21. So if in case that we get 0 in here, is we can use it in our public key. So in this case, in 108 mod in 29 is equal to 21. There's a remainder of 21, sorry. So 29 is totally acceptable. So our public key is equal to 29.
Step 5. And for the last step in generating key is to select a private key, or let's call it D. So in private key, it only match in one condition, which is if we multiply the private key and the public key divided by T, or totient must be result in remainder of 1. And now we have here our example, and we're going to use the formula, which is D multiplied to E and mod by T is equal to 1. So in here, let's try our private key is 41 and multiply it in our public key, which is 29, and mod it in our totient, which is 108, and we get the result of 1. So 41 meet condition. So our private key is 41. So now we already have our private key.
So now that we have the public and private keys, let's actually use them for encryption and decryption. For encryption with RSA, first we will take the message that will be encrypted and raise it to public key value. Then let's figure out the remainder when divided by n, and that's going to get the ciphertext to decrypt. And now we will take the ciphertext and raise it to the private key value and figure out the remainder when divided by n. And if RSA works the way, that will be the thing that we should get the same message when we started earlier. Now let's go ahead and test it. So we're going to use a message value of 60. So 60 is going to be our starting message, and we're going simply step through these formulas to prove how RSA works. So let's start by encrypting the public key and then seeing if we can decrypt with a correlating private key. So to encrypt with the public key, we will going to take the message, which is the 60, and raise it to 29, which is the public key. And let's figure out the remainder when divided by 133. So the result is 86, which means 86 is the ciphertext of encrypting this message, 60 with the public key, or with this public key. Now we will be able to use the description formula and the private key to decrypt that back into the original message. So 86, which is the ciphertext, and raise it to the 41st power, and then figure out the remainder when divided by 133. And that's it. It was indeed able back to 60. Now, this proves that RSA works the way it does. We will be able to encrypt the message of 60 with the public key and decrypt the resulting ciphertext with the private key. But remember that RSA is commutative, which is you can encrypt public key and decrypt in the private key, or you can encrypt with the private key and decrypt the public key. Okay, so let's switch the public key and the private key in our formulas and see if we can still encrypt and decrypt and result with the same message. So let's encrypt the same message. This time we're going to do the encryption with the private key and description with the public key. For encryption with the private key is 60. So 60 is our message raised to private key value, which is 41. And let's figure out the remainder when divided by 133. And the answer is 72. This is now the ciphertext after encrypting with the private key. So let's see if we can take the ciphertext and decrypt with the public key. Now, take the 72, which is the ciphertext, and raise it to public key of 29, and then divided by 133. So the answer is 60, which means it lands back to the original message. So now we just have proven the RSA we've shown you. So that is behind the math of RSA.